Hey everyone, ready for another deep dive? Whether you're brushing up for something specific or just love a good math mystery, I think you're going to enjoy this one. Today, we're looking at a sequence that's got ties to, well, a lot more than you'd think at first glance. Prime numbers, computer graphics, maybe even some unsolved problems out there, all connected to this thing called A000051. Catchy name,
That
right?
definitely rolls right off the tongue.
But seriously, to guide us today, we've got a couple of sources. First, excerpts from the online encyclopedia where the sequence lives, officially, I guess you could say. And then someone's put together this whole study guide about A000051.
Yeah, sound like we've got a fellow enthusiast out there.
Sure. And just to pique your interest even more, check this out. One of the numbers in this sequence is the only Halliard square, like ever, proven way back in the 1600s. And it's also got something to do with those trippy fractal images, the Hilbert curves.
Sensing a theme here. This simple sequence might have some pretty complex and far-reaching implications.
Okay, so let's break this down. What exactly OEIS A00000051? Lay the foundation for us.
Right, so at its most basic, it's defined by the formula AN equals 2n plus 1.
Okay, so 2 to the power of n plus 1. Seems simple enough.
Exactly, and you can see that when you look at, say, the first few terms, if n is 1, well, 2 to the 1 is 2, plus 1 gives us 3. If n is 2, we get 5, and if n is 3, we get 9.
Gotcha. So pretty easy to calculate those first few. But the study guide also mentions something called a recursive definition. What's that all about?
Recursion. That's a way of defining a sequence where each term depends on the one before it. In this case, it's A02, and then for any n greater than 0, AN equals 2AN-1, 1.
So instead of relying on exponents, we can just kind of build the sequence step by step.
Exactly, precisely. Think of it like a chain reaction. Let's try it out. We start with A0, which is 2. To get A1, we double that, 4, and subtract 1, giving us 3. To get A2, we double 3, that's 6, and subtract 1, which is 5. See, same sequence, but a different approach.
Huh, 2 different paths, same destination. Interesting. Now, the study guide also points out something fascinating about this sequence's binary representation. It says something about, let me quote this directly, a 1000.001 pattern.
Right, the binary representation. This really highlights the structure of this sequence. Remember, in binary, each position represents a power of 2.
Right. Like 101 in binary would be 5, because it's 1 times 2 to the power of 2, plus 0 times 2 to the power of 1, plus 1 times 2 to the power of 0.
Exactly. So when you look at the binary representations of the numbers in our sequence, you get this striking visual. From the second term onwards, it's always a leading 1, then a bunch of zeros, and it ends with another 1.
So like 3 is 11, 5 is 101, 9 is 101, and so on.
Precisely. Almost like a mirror image of the powers of 2 in binary, which would be 1, 10, 100, etc. And this visual contrast is actually significant. There's even a separate sequence for numbers with that opposite binary pattern. The leading 0 and all those 1s.
Hold on, a whole other sequence dedicated to what visually looks like the opposite of our sequence. Things are getting really interesting. It's like we're looking into a mathematical mirror or something.
It really highlights how subtle variations can lead to entirely new mathematical objects, But the connections don't stop there. This sequence also has fascinating ties to prime numbers, specifically Fermat primes.
Now you've got my attention. I've heard of Fermat primes, but remind me, what makes them so special?
So they're prime numbers of a very specific form. 2 raised to the power of 2 to the n plus 1. Sound familiar?
Wait, so some of the numbers in our sequence are also Fermat primes?
Exactly. And guess what? They even have their own sequence in the encyclopedia, sequence within a sequence. And it gets even more interesting. There's this historical proof from the 1600s by a mathematician named Bessy, and he showed that only one number in our entire sequence is a perfect square, the number 9.
Okay, hold on. Let me get this straight. We've got this sequence, pretty simple formula, but it's somehow connected to these special prime numbers. It's got a unique binary representation, and it even hides this mathematical fact that was proven centuries ago.
It just goes to show, even seemingly simple mathematical concepts can have incredible depth, and they can connect to this whole web of fascinating ideas. But we're just getting started. Remember those Hilbert curves we mentioned? Well, there's a surprising link there, too.
Oh, yeah, the fractal images. How does a sequence of numbers connect to something visual like that? I'm all ears.
So imagine a curve that continuously folds and twists to fill an entire square. No matter how many times you repeat the process, that's a Hilbert curve in a nutshell.
And what's fascinating is that the length of the curve after each fold corresponds exactly to the numbers in our sequence.
Whoa, so as the Hilbert curve gets more and more complex, fills more of the space, its length jumps to the next number in A00000051. That's mind-blowing. And it gets even more interesting. The Hilbert curve isn't just a mathematical curiosity. It's got real-world applications. Things like image processing and data storage use it.
Wait, so this sequence isn't just some abstract mathematical concept. It has, like, real-world uses. Okay, now I'm really intrigued.
This is just the tip of the iceberg, really.
Hmm.
We've also got Pisano periods to explore, and then there's this whole mystery of how Cunningham numbers are connected to all this.
Right.
But before we journey any further down this mathematical rabbit hole, maybe take a moment to process what we've uncovered so far.
Yeah, good idea. I need a minute to wrap my head around all these connections. All right, I think I'm ready to keep going. We were about to dive into Pisano periods, and those sounded, well, seriously mysterious.
Oh, they are fascinating. So imagine taking the Fibonacci sequence, that classic 1, 1, 1, 2, 3, 5, 8. Each number is the sum of the two before it. Now imagine dividing that sequence by another number.
Okay, so let's say we divide the Fibonacci sequence by, 3.
Exactly. Now focus on the remainders after each division. You'll find that they form a repeating pattern.
Wait, really? So if we divide the Fibonacci sequence by 3, the remainders would, like, cycle through a specific set of numbers over and over.
Precisely. And the length of that repeating pattern, that's what we call the Pisano period for that divisor. What's interesting is that our sequence, A00000051, it actually has a connection to these Pisano periods.
Okay, now you have to tell me more about that connection. You can't just drop a bombshell like that and not elaborate.
Well, the source material hints that a certain type of prime number is involved in determining the lengths of those Pisano periods, specifically when our sequence is the divisor. It doesn't go into much detail, though, kind of leaves it as a puzzle for us.
A puzzle, huh? Challenge accepted. I'm definitely going to look into that. But first, we have one more mystery on our list, those Cunningham numbers.
Yeah, this one is even more of a head-scratcher, to be honest. The source just mentions them in passing. It doesn't really explain how they connect to A00000051.
So another breadcrumb trail to follow. What can we figure out based on what we know about Cunningham numbers?
Well, they have that form, b to the power of n plus or minus 1. Kind of like generalized Fermat numbers, you could say.
And since our sequence is all about 2 to the power of n plus 1, could there be some overlap there? Maybe some Cunningham numbers also appear in our sequence.
That's a sharp observation. Or maybe the connection's deeper, like in the shared exponential structure of both types of numbers.
Okay, now I'm really curious. It feels like every time we think we've got a handle on this sequence, there's another layer of complexity.
And that's what makes it so fascinating, right? What seemed like this simple formula has turned into this gateway to prime numbers, fractals, binary patterns, and now these hints about Pisano periods and Cunningham numbers.
It's like a reminder that even in math, things are often connected in ways we might not expect at first.
Absolutely. A 000005 isn't just a sequence, it's like a microcosm of how interconnected mathematical ideas really are.
So we've explored the binary quirks, the prime number connections, that mind-bending geometry of the Hilbert curve. And now we've even got hints about even more mysteries lurking beneath the surface. What does it all mean? Where do we even go from here?
Well, that's the beauty of it, isn't it? We've opened up this whole world of possibilities. We've seen how this sequence connects to so many different areas of math, and there's still so much more to explore.
It's like we've climbed to the top of a mountain, and now we can see all these other peaks in the distance, just waiting.
Exactly. And who knows what other mathematical treasures are waiting to be discovered. Hidden within this seemingly simple sequence, maybe you listening will be the one to uncover the next big connection.
Wow, it's amazing to think we started with just, 2 to the n plus 1, that simple formula, and look where we ended up. Prime numbers, fractals, binary patterns, and then all these hints about even more connections, stuff we haven't even fully untangled.
It really shows you the power of just being curious, and that even in math, a field that seems so well defined, there's always more to find, more to discover.
And what's really cool is that this isn't just some abstract exercise. We saw how A000051 actually pops up in the real world, like with image processing and data storage.
Absolutely. It really drives home the point that these theoretical concepts, they can have practical implications, ones that we might not even grasp right away. It's like knowledge is interconnected. You never know where one little thread might lead.
So for our listeners out there, what's the big takeaway from all this? What do we hope they walk away with after our deep dive?
I think the biggest thing is that there's always more to learn. It's easy to dismiss something as simple, basic. But we've seen with A000051, even the most fundamental idea can have Surprising depth. A lot of complexity.
Like one of those optical illusions, you see one image, but then you shift your perspective, bam, a whole new picture emerges.
Exactly. So we encourage everyone listening, approach the world with that same curiosity, that same wonder. Don't be afraid to ask questions, dig a little deeper, look for those hidden connections.
Maybe one of our listeners will be the one to crack the code of how Cunningham numbers fit into all this. Or maybe they'll find a connection, something totally new that we haven't even thought of.
The possibilities really are endless, and that's what's so beautiful about math, about knowledge itself. It's a journey that never truly ends. You're always exploring, always discovering.
So to everyone listening, keep those mathematical minds buzzing. Challenge your assumptions. Look for patterns and never underestimate the power of a simple question. Who knows what amazing things you might find hiding just beneath the surface. Until next time, happy exploring.